Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. Today's video is about custom layer in Tensorflow Keras and also building a simple model after creating a custom layer. Now, a layer is a data processing module that takes as input one or more tensors and that outputs one or more tensors. The fundamental data structure in a neural network is this layer, and so also one of the central abstraction in Keras is a layer class. A layer is a class in Keras that receives some parameters, passes them through states and computation, and at the end gives you an output as required by the neural network. Every model architecture contains multiple layers, be it a sequential or a functional API. Now, the most important thing to remember is a layer has two elements in it. Number one is state, which are the weights, which can be trainable or non-trainable, and layer also has some computation, which is the forward pass calculation. Now, some layers are stateless, but more frequently layers have a state. Now, in this slide, let's quickly take a slightly more detailed look at the state and computation definition. So, states are mostly trainable features which are trained during a model.fit. In a dense layer, the states constitute the weights and the bias. These values are updated to give better results as the model trains. In some layers, a state can also contain non-trainable features or non-trainable weights. And these weights or tensors actually are learned or trained with stochastic gradient descent, which together contain the network's knowledge. And this stochastic gradient descent happens during the execution of the model.fit function. And now the computation. Computation helps in transforming a batch of input data into a batch of output data. In this part of the layer, the calculation takes place. In a dense layer, the computation does the following calculation: y equal to weights multiplied by the x vector, which is the input vector, plus b. And this whole expression on the right side returns me the y. So y is the output, x is the input, and w are the weights, and b is the bias term here. Now, given weights in a layer are all about tensors, so let's quickly understand the shape and the rank of a tensor. So mostly we will be dealing with rank 0, rank 1, rank 2, and rank 3 tensors. And this is a representation of those ranks. So let's check that rank 0, which is this, is a tensor, is a scalar value. That's a single number that has magnitude but no direction. Rank 1 tensor is a vector. It has magnitude and the direction. Rank 2 tensor is a matrix. It is a table of numbers. So these on the left, each row, you can think about each sample. Each row is representing each sample, and then each column is representing each feature. So this is a rank 2 tensor, and rank 3 tensor is a cube of numbers represented by this last image. So basically, there's no shape for rank 0 tensor because it has no dimension. The shape would hence be empty array or a single empty array. And rank 1 tensor has a shape here. In this case, it's a shape of this, which is a single array with the number being 3 inside. And rank 2 tensor, this one will be represented by 3 by 6 matrix, that is 3 rows and 6 columns. And this one, that is rank 3 tensor, has a shape of 2 by 2 by 2, that is each axis has 2 elements in it. Now, for practical example, rank 2 tensors, that is this one, which is a matrix of so many rows and so many features, is mostly processed in a dense, fully connected layer or dense layer, as it is called in Keras. And then rank 3 tensor, this is mostly seen in sequence data, which are stored in rank 3 tensors of shape, samples by time steps, by features, and is typically processed by recurrent neural networks such as LSTM or one-dimensional convolution layer, that is conv1D. And rank 4 tensors, we don't see that in this particular slide. Rank 4 tensors are mostly about image data, and that is usually processed by two-dimensional convolutional layer. And now about the topic of today's video, which is about creating custom layer in Keras. Now, since Keras utilizes object-oriented programming, we can actually subclass the layer class and then insert our architecture definition inside that child layer class. So basically, first take a quick look at how a parent layer and child layer overall created in Keras, and this is the structure. So basically, I have a parent layer and then a child layer which is inherited from the parent layer. And the way I call the child layer, so the child layer is basically a custom implementation of the parent layer. And the way that I call is, for example, if I have X input, then the child layer is executed by passing some the arguments to child layer and also passing the X input, and then I get X output. So in this example, the child layer class instance is called directly with the input X input, like in this line. And this action calls the underscore underscore call this function found in the parent layer of the child layer. And this underscore underscore call function in the parent class in turn calls the diff call function in the child layer class, which defines the logic of the child layer. And now I'm going to actually create a custom layer in Keras. And if you look at the documentation of Keras, you will find this statement that I've written here, very clearly written in the official documentation page of them, that each custom layer class must define three methods: init, call, and also usually the build method. The build method is not compulsory, but most often it is indeed written. So the init assigns layer wide attributes, that is a number of output units. If you know the input shape, you can also initialize the weights in the constructor as well. The build is not strictly required, but implementing it is a best practice. Defining this method allows you to instantiate weights lazily, which is important if you don't know the size of the input when you initialize a custom layer. And finally, the call method. Call method defines a forward pass. That is, call method handles the calculation of the forward pass in a neural network. As long as these operations are differentiable within the call method and the weights are set to be trainable, TensorFlow will handle backpropagation for you. And so this is the main 3 points that Keras official documentation actually recommends. And following these, I have already now I'm going to define the actual custom layer in Keras, and this will be my code. Okay, this is my code for building the custom layer. So so you can see this is this class, this child dance class. This is what represent my custom layer, and this is inheriting from the main layer class of Keras, that is keras.layers.layer. I've already imported the Keras library with this line here, and I have also imported the TensorFlow STF. And then in the first argument, I'm doing keras.layers.layer. It will make my child layer class being inherited from the parent layer, that is from the main layer class of Keras. And now for the next 4 or 5 minutes, I'm going to go through each part of this code. That is, what is this init method is doing here in the child class, then how exactly the build method is forming the weights with the add weights function, and what this add weight function indeed is doing, how to assign the input dimension, that is the input shape in a child layer class in Keras, and also how exactly the call function is doing the calculation. So let's do that. So the first point is understanding about why we are doing this init method is part of the class constructor. And to understand it, first take a quick look at how method resolution order works in Python. So method resolution order is also called MRO. And 1 second. Okay, so this is a quick slide on MRO. In Python, the method resolution order is from bottom to top and left to right. This means that first the method is searched in the class of the object. If it is not found, it is searched in the immediate superclass. In the case of multiple superclasses, it is searched left to right in the order by which it was declared by the developer. Now let's take a look at this example, that I have a simple definition of a class, diff class C, and that takes two arguments B and A, and under these some code comes. So in this case, the MRO would be C to B to A, because B was mentioned first in the class declaration. So method resolution order defines the order in which the base classes are searched when executing a method. First, the method or attribute is searched within a class, and then it follows the order we specified while inheriting. Now, this whole theory about MRO is very important for understanding this line, super.init. So let's understand this line for a general Python class definition, that what exactly this init method clubbed with super is doing and how it works. So when I call an init method in the class definition like this, that super.init, it means that calling the init method of the super class as if it were a method of the current class, since the current class is derived from the superclass. In other words, it means to call a bound init method from the parent class that follows a super's child class, the one that defines this method in the instance's method resolution order. So super lets you avoid referring to the base class explicitly. And when you write a class, you want other classes to be able to use it. Super makes it possible by making it easier for other classes to use the class you are writing. Now, when another class subclasses the class you wrote, it could also be inheriting from other classes, and those classes could have an init of their own that comes after this init based on the ordering in the MRO, method resolution order. Without super, you would likely hardcode the parent of the class you are writing. This would mean that you would not call the next init in the MRO, and you would thus not get to reuse the code in it. So if you are writing your own code for personal use, you may not care about these distinctions, this kind of architecture. But if you want others to use your code, using super is one thing that allows greater flexibility for users of the code and for sharing the code. Now coming back to the init method defined in our child dense layer, which is inheriting from the keras.layers.layer, which is a main keras layer. So init is a first method in this subclass that will help to initialize a class, and init accepts parameters and converts them to variables that can be used within the class. This is inheriting from the main layer class of Keras and hence requires some initialization. This initialization is done using the super keyword here. And units are activation of the arguments that init takes. Units is just a local class variable. This is analogous to the number of units in the dense layer, and activation here represent for the activation function. So to add an activation to my whole network of this layer, we need to specify this in the init method itself. Either a string or an instance of an activation object can be passed into this activation. It is set to default as none. So if no activation function is mentioned, it would not throw an error. Now the build method. Build is the next method in the class. This is used to specify the states. In the dense layer, the two states required are W, that is weights, and B, that is bias. When the dense layer is being created, we are not just creating one neuron of the network's hidden layer, but multiple neurons at one go. Very important to remember this. So if I pass 32 as a value for this unit argument, which is an argument out of the init method, then 32 neurons would be created. And then each of these 32 neurons in the layer needs to be initialized and given some random weight and bias values. TensorFlow contains many built-in functions to initialize these values. Here, for initializing the weights, I'm using random normal initializer function here with these parameter initializer equal to random normal. So with this, TensorFlow will initialize the weights normally from randomly using a normal distribution of values, and self.w contains the states of the weights in the form of a tensor variable. And the shape of these tensor variable, that is the shape of my weights, is defined by this parameter, that is shape equal to input dim and self.units. I will explain these two things in a second. Before that, just move on to the creation of the bias variable as well, and then I will come to a separate explanation of these input shape and how it is implemented after this. So I'm initializing the weights here, and in the next line I'm also initializing the bias. And for initializing the biases, TensorFlow's zero initializer function is used. That is initializer equal to zeros. This sets all initial bias values to zeros. That is self.b is a tensor with a size same as the size of the units. By default normally it's 32, and each of these 32 bias terms are set to 0 initially. Now another thing I should do here, that is I'm adding another parameter called trainable equal to true to both of them, that is to both weights and biases. This also sets these weights and bias terms to be trainable. That means these terms will be updated as a training moves forward. And now about these input shape parameter that I pass while creating the weights, that is initializing the weights to my add weight function, and that will define the shape of the weights, and is extremely important because while doing your real life project in deep learning using Keras, TensorFlow or PyTorch, whatever framework you use, matching and working with the shape variable, that is shape of the tensor you pass to your network, is an extremely important point. And many times this will be one crucial factor that will make or break your model, because making these shapes parameter compatible and deciding on the shape parameter perfectly is really important in any deep learning project. So quickly let's take a look at a slide that I made for understanding these input shape parameter in my custom layer function. So the input layer is just a tensor, that is the input shape is just a tensor having the same shape as your training data. It's a starting tensor you send to the first hidden layer. Example, if you have 30 images of 50 by 50 pixels in RGB, that is 3 channels, RGB channels, the shape of your input data is 30 by 50 by 50 by 3. Then, and how this numbers is coming, 30 images, 50 into 50 each, that is 50 by 50 pixels, and then I have 3 channels for 3 RGB color channels. And then your input layer tensor must have this shape. Now the input shape is the only one you must define, because your model cannot know it. Only you know that as a data scientist and based on your training data, and that's why you have to input that at the first stage of your model. All other shapes are calculated automatically based on the units and particularities of each layer, meaning given the input shape, all other shapes are results of layer calculation. Now take another example, input shape as given as 728 and then just a comma, that is it's a single scalar value given as an input shape. So this means that each sample has 728 values. The comma does not create a second dimension, it's just Python notation for creating a tuple that contains only one element. Input shape 728 with the comma is the same as batch input equal to batch size comma 728. So in a single sentence, the input shape parameters can be defined as that input shape parameter simply tells the input layer what the shape of one sample of your training data looks like. Adding it to your input layer will ensure that a match is made. And now also a quick word on this add weight function. This adds a new variable to the layer. It is a method for layers and it creates a TensorFlow variable representing some mutable values in the layer. If you look at the documentation for how to add custom layers, they definitely recommend using add weight function for this purpose. So in the documentation you can actually see that many more parameters that this add weight function actually takes has been mentioned very well. So in my next cell actually an example of using the build method and using add weight function to create the weights. And here I'm just for showing as an example, I'm using some more parameters that add weight function takes. So the first one, it takes a string as its name. Then shape, of course, we have used in the above as well, that it takes a shape parameter which defines the shape of the tensor that it will output. And initializer, very important. This actually initializer actually defines a way to set the initial random weights of Keras layers. Here first I have used in this case, that is in my custom layer function, I have first used the initializer to be random normal. That means that initializer generates tensors with a normal distribution, and then in the next one I have given the initializer to be zeros. That means initializer that generates tensor initialized to 0. So overall, the add weight method gives you a shortcut for creating weights. It's a good practice to create weights in a separate build method called lazily with the shape of the first inputs seen by your layer. And now finally, the third and the last method in our custom layer, which is this method, call. Now call is a last method that performs a computation. In this case, as it is a dense layer, it multiplies the inputs with the weights, adds a bias, and finally returns output. The matmul function here, which does a matrix multiplication, is used as self.w and self.b are not single scalar values. They are actually tensors, and that's why I'm using tf.matmul. And now a natural question that may come to your mind is, what is the difference between these underscore underscore init method defined in this subclass and the underscore underscore call method that has been defined in the original base class of Keras, that is original layer class. Remember, our child dense class is defining this init, but the child dense class is actually inheriting from the original layer class. This is the base class from which this child dense is being inherited. So this original base class layer has a method called underscore underscore call. And what is the difference between that call and this init method? So let's quickly look at that. And this is that difference. That is, the underscore underscore init defined in this subclass method is used when the class is called to initialize the instance, that is when the instantiating the class, while the underscore underscore call method that has been defined in the parent base class is called when the instance is called. So this underscore underscore call is a template to call the already instantiated class to do something. And now the next natural question that will come to your mind, that why does Keras use two different type of call method? That is, one is these underscore underscore call method that is defined in the original base class of layer in Keras, and the call method that I defined here in the subclass in the child dense layer class. So let's quickly look at a very beautiful Stack Overflow question that has answered this question very beautifully. That here the original question was exactly this: why Keras use call instead of call? And this is that answer. Definitely go through the entire. Okay, this is the only answer that it has been given. And yeah, so I found this answer pretty beautiful, that basically in Python, when you call an instance from class A using class A and then invoke it or execute it, it is equivalent to class A dot underscore underscore call. So it seems reasonable to use underscore underscore call instead of call in the case, right? However, the reason we use call in our subclass, that is in our child layer class, is that when tf.keras calls a model or a layer, it has its own inner operations which are essential to keep its inner structure. As a result, it exposes a method call in the subclass for customer overloading. That is, the original underscore underscore call calls this call which has been defined in the subclass, as well as some inner operations. So when we reload the call inheriting from tf.keras.model or tf.keras.layer, we can call our custom code while keeping the original tf.keras's inner structure. For example, if your input is a numpy array instead of a tensor, you don't need to transform it manually if you write customer code in call function. But if you overwrite the original underscore underscore call function that has been defined in the base parent class in layer or model, it would be a problem since some inner operations of TensorFlow will not be called in that case, and that's why a numpy array may not be acceptable to whatever you are trying to do in your network. Now my custom layer is completely written, so I am ready to implement my custom layer to see that it takes some input and gives me some output. And remember, both my input and output will be some tensor. So let's write the code. I'm going to implement my child dense class that I just wrote, and the first one it takes is units equal to 32. I'm giving the pretty much the default value of 32, and the next one is activation function, activation equal to tf dot neural network dot relu. I'm giving it a relu activation function, and then input tensor. Input tensor would be f dot I'm going to give it I'm going to give it a shape of 2 and 784. So tf dot ones and shape equal to, it will be a tuple of 2 and 784, and output shape will be calculated by my child dense function. So let's implement my dense and give it my input tensor, and that should be my output tensor. Let's see if I run this code. Awesome. So I got output tensor. This is the output tensor. Let's quickly check their shape. Output tensor dot shp, and I got a 2 by 32 matrix, or 2 by 32 two-dimensional tensor as my output. So now that my simple custom layer is looking to be working perfectly, and the code just worked, so now I am going to do a full model using that same custom layer that I just built previously, that is child dense. And before building the model, I have to create some dummy data, and I'm going to create a two-dimensional data, that is the data will have x and y axis, so let's do that first. And this, remember, the Keras layer class has the same basic API as a model class. Model has more methods exposed, of course, like a fit, evaluate, save. But in the same way that a layer can be composed of other layers, a model can be composed of other models and layers. This is useful when you borrow functionality from a pre-trained model. Now my two-dimensional dataset that I'm going to create now, it will have few negative samples and few positive samples. That is, I'm going to create two sets of dataset, and these two dataset will be very nicely linearly separable, so that I can clearly see the positive samples being separated from the negative samples. And also, I'm going to generate each classes of points by drawing their coordinates from a random distribution with a specific covariance matrix and a specific mean. Now, intuitively, the covariance matrix describes the shape of the point cloud, that is shape of the data set that I'm going to generate. Here, the point cloud means in the cloud, each data point is a point. And the mean of this point cloud describes its position in the plane. I will reuse the same covariance matrix for both the point clouds, but I'm going to use different mean for these two data sets. So it will mean that my point clouds will have the same shape but different positions. And here is a code. So first I'm just defining the number of samples in each class. That I am defining it to be 2000, and then this is the first line is for creating my samples negative. These will hold, these first set will hold all the data samples with for negative samples, that is, and I'm using multivariate normal, so I'm drawing the entire sample from NumPy's multivariate normal distribution and assigning the mean to be 0 and 3, and covariance, for the covariance matrix I'm assigning this matrix 1 and 0.5 and 0.5 and 1, and size of course will be the total number of samples in each class. And exactly the same kind of code for generating the positive samples as well. In only difference is here the mean is different. In the first set I had mean of 0 and 3, and the second one mean of 3 and 0. Now let's quickly run this cell to check the shape. Yep, so I have their shape as expected, 2000 samples, 2000 rows, and it has two columns or two features. And now let's stack these samples positive and samples negative in vertically. So I get a single data matrix with a shape of 4000 by 2, because I have 2000 data into 2000 samples in negative and 2000 samples in positive. And this is the code. So I'm creating a new variable x inputs. This will hold my entire input data, and then I'm vertically stacking the samples, negative samples and positive samples, with np.vsstack, and I am stating the type as type to be numpy float32. Let's run this code. Perfect. So I got a data matrix with 4000 rows and 2 columns. And now I'm going to also generate, I have to generate the target values. My target variable or vector will be an array of ones and zeros, and of the shape 4000 by 1, because I have 2000 positive samples and 2000 negative samples. And also another point, that the target I0 is 0 if input I belongs to class 0, and target I0 is 1 if input I belongs to class 1. Yeah, and now this is the code for creating the target variable. And of course I have to vertically stack the negative samples and the positive samples using np.vsstack. And here is that line. So y target is a variable holding on the target vector, and all I'm doing, I'm creating np.zeros and np.ones, and in each case I'm creating that many samples of zeros and that many samples of ones, and my sample number remains 2000, and d type is again float32. Just run it, and okay, let's print this y target. Awesome. It is a vector of 0 and 1s, and yeah, that's what I want. And before proceeding further, I want to do a quick scatter plot of my input data, that is x input. But before that, let's check the what kind of data it holds. X input. Remember, x input we created by vertically stacking my samples negative and samples positive with np.vsstack, and it has a shape of 4000 by 2. Now let's just print my input variable. That's not x input. What was the name? X inputs. Okay, there's an a's there. Yeah. All right, so this is the array of my x input. So it has 2 columns, and it's a 2-dimensional data. Okay, fantastic. Now I am ready to do the scatter plot. Let's do my scatter plot, and this is the code for my scatter plot. All I'm doing to plt.scatter, I'm passing first x's value, that is all these values, and then the next value with the comma I am passing the second x's value, and that's why after the comma I am using 1. To actually check understand this concept, if you just print x inputs colon and then 0, that means it will print the entire first column. Yes, so see 0.3344 is my first value, then the next value will be -245, -245, etc. And if I do the same with 1, it will print a second column, 2.933, yes, and 1.87, 1.87, perfect. Okay, all right, I can delete this cell. All right, so in my scatter plot, I'm just passing these 2 axes of data, the first axis and the second axis, and then plt.show. Let's run it. Awesome. I got a very beautifully linearly separable scatter plot. So all the negatives and positive samples are very well separated, and okay, that's beautiful. And now let's move on to my next chunk of code. Now let's start compiling our model, because the data is completely ready, and let's compile a sequential Keras model. So Keras.sequential, and to it I'll be passing a layer, and I'll be passing a dense layer. So Keras.layers.dense, I'm passing it input of 1, and with that I'm ready to compile, and the compilation code would be this. let's understand this piece of code one by one. The compilation step is about configuring the whole learning process of the model, because once the model architecture is defined, you still have to choose three more things, which is loss function, optimizer, and metrics. And my whole model architecture here was defined in this line. Remember, here I'm not using anything complex, I'm just using a single dense layer, and this is a line where my model was architected. And now in the compile phase, I am taking care of the three other things, that is loss function, optimizer, and metrics. So the first is optimizer. What the optimizer does is it determines how the network will be updated based on the loss function. It implements a specific variant of stochastic gradient descent. And then the loss function or the objective function, here I'm mentioning the loss function to be a mean squared error. So this is the quantity that will be minimized during the training. It represents a measure of success for the task at hand. And the last one is metrics. And this matrix actually, it's just a measures of success you want to monitor during the training and validation, such as classification accuracy. Unlike the loss, training will not optimize directly for these matrices. As such, metrics don't need to be differentiable. And again, if you are wondering about what is the difference between loss function and metric in this Keras model that we just built, I refer you again to this beautiful Stack Overflow question here that was asked exactly the same question, and this answer very clearly tells the loss function is used to optimize your model. This is the function that will get minimized by the optimizer. A metric, on the other hand, is used to judge the performance of your model. This is only for you to look at and has nothing to do with the optimization process. Now that my model is compiled, I'm ready to train the model by using .fit function of Keras. But before training the model, I have to do the most important part of any training, which is splitting the dataset into train dataset and validation dataset. Because otherwise, if I train the entire dataset, my model can just remember the mapping between the input and the outputs, and there is no point in calculating the loss or the evaluation metrics on the same dataset. So during the training, I have to keep a particular part of the dataset which is completely unseen during the training portion of the model. So let's split the dataset, and this is my code. Yeah, and I'll go through each part of this code line by line. So first, what I'm doing is I'm shuffling the entire dataset indices using the numpy random and dot permutation function. So I have a list of indices which is entirely shuffled, and then I am with the shuffled indices, I'm creating two new variables for my inputs and for my targets, and passing to the original data these shuffled indices, so that I now get a data set of arrays which are completely shuffled. And then first I'm creating, and this is now the important part, which is about the actual splitting. And so my target is to split to keep 30% of the data set as a validation set and the rest 70% as training set. So number of validation samples is just multiplying the entire length of x inputs with 0.3 and then taking the integer form of that. And then with the number of validation samples, which is 30% ready at my hand, then that I am with that I'm using the slice notation of Python to split the dataset. That is, first I'm keeping the first 30% for validation. That is, I have to extract or slice the dataset by at that dividing point. That is, I have to take the first 30% of the dataset for my validation set, validation input, and also for my validation target. And this line is doing just that. Actually, I have put the comment. In the comment, you can see what this is the actual signature of the slice notation, that I have a list, and if I pass colon and then 5, then items from the beginning through 5 minus 1 will be extracted. That is, this expression will return me the first 4 items, that is 0th item up to 5 minus 1. And so this line will give me all the inputs values, all the input array values starting from the beginning of the array up to the number before these number validation samples. And I'm doing the exactly same for validation targets. So this will be my validation set, that is validation input and validation target. And I also have to do the training inputs and training targets, and exact same code. Only difference is now the colon is at the end. That is, I am starting from this value and going up to the end of the array. That would be my training inputs. And similarly for the training targets, I am starting from this index and going up to the end of the array. That is, I am taking all the rest of the values after my validation set. Let's actually print the shape of them. So let's actually run this code, this cell, and now I'm going to print these new splitted array that I just created. Shape. Okay, so the validation inputs to 1200 by 2 makes sense, and validation target also should be, oh sorry, let's .shpe. Yeah, validation target is also 1200 number of samples, and of course the number of columns is 1 because it's just a single value of target. And similarly I will have .shpe, and then also training targets.shpe. Run this code, and okay, print statement. Without print, it will only print the last expression. So now it will print the both of them. Run this code, and I'm getting 2800 in my training inputs, and number of columns is 2 because I have 2 features, and for the targets is again 2800, and of course the column will be 1. Awesome, that makes good sense. I can actually delete this cell now, or maybe not, just keep it. So after splitting these training inputs and training targets, these will be the two data or two NumPy array or TensorFlow object that will be passed to my training model, that is to my fit function. So let's understand the fit function, because now the data is completely ready to be fed into the model for training. So after compile, remember we have already compiled the model in previous step here. That is, first we define the architecture of the model here in this line. It's a super simple architecture. There is no hidden layer and no stacking of layers. It's just a single dense layer of Keras. And then I ran this compile function. So my model and data is completely ready to be compiled now. That is to be trained now with the fit function. So let's understand the fit method. After compile comes a fit. The fit method implements the training loop itself. These are its key arguments. The first one is data, inputs and targets to train on. It will typically be passed either in the form of a NumPy array or a TensorFlow dataset object. The number of epochs, that's another parameter to the fit function. That is how many times the training loop should iterate over the data passed. And another important parameter to fit function is batch size. That is the size to use within each epoch of mini batch gradient descent, the number of training examples considered to compute the gradients for one wait update step. All right, now I have made a quick slide. Let's look at them. So this is the overall representation of model.fit, and it takes I have passed 4 arguments here: inputs, targets, epochs, batch size. So the input example can be either NumPy array or TensorFlow objects. Corresponding training targets also will need to be passed, which again can be NumPy array or TensorFlow objects. Epochs is just a number of epochs. I have put here 5. It can be anywhere 10, 50, etc., depending on the power of your machine that you are running on. And so that means epochs means the training loop will iterate over the data 5 times here. And with each epoch, your accuracy of the model is supposed to be enhanced up to a certain point. And lastly, the batch size, which I have given 128. That means a training loop will iterate over the data in batches of 128. So your training may have millions of samples, but for each training loop 120 will be considered, and that's the way your machine can accommodate the huge number of batches, huge number of samples for large scale data set. So now let's run the fit function. Before that, quickly check the shape, that is the number of samples of our training samples. So we have 2800 samples in our training data set, and the code for my actual training will be just this. That is the model is already compiled, and on top of that I'm passing a .fit function. To that I am passing training inputs and training targets. So this is my X data and this is my Y data. And epochs I am passing 10, that is I'll be running for 10 epochs. Batch size I'm giving a very small number here, 16, because my whole data set itself is 2800 in training. And the validation data, this is another important parameter in the fit function, because evaluation of the model, that is Keras, will run internally an evaluation of your training, and that will be done not on your training set but on your validation set that we did previously. So validation data will be my validation inputs and the validation target, that is just the corresponding to these training inputs and training targets. We already split the data set, kept 30% of the data set to be my validation set, and this is that being used here. That validation data I'm passing as a tuple for my inputs and for my validation targets. And just quickly check again so that we don't forget what they are. Remember, in this cell we created these validation inputs and validation targets, and also we checked their shapes here. Let's check the shapes another time. Print, run this cell. Yes, so I have 1200 number of validation samples. Okay, now let's run the fit. Yep. Okay, it ran very quickly because it's a very small data set. Indeed, 2800 number of training samples is actually nothing for the real world. In the real world, it probably will be dealing with millions of samples. So anyway, it ran the training pretty fast, and I have held the entire training output in a variable called history, because now this history variable will have some pretty important information after the training is done. So this history now has all the important parameters it has got within itself, and I'm going to extract it. But before that, let's print the history variable to check what this is all about. Okay, so it says callbacks history at okay, it did not give me anything. Let's print in another form. Actually, history did not give me anything because it has a object called history within itself, and that object has all the important information. So I actually have to print it like this: history.history, and this actually has all the model training parameter after the training in a dictionary format, that is in key value format. So let's print it. Awesome. This is exactly what I needed. And that is, I have the loss, I have the binary accuracy, I have the validation loss. Validation loss is called val loss here in Keras. And you are seeing so many values because these important values like loss, binary accuracy, they are all held for each epoch. Because during the model, Keras do so many things, and one of the important thing is that they keep a track of the result of the training after each epoch. So all these results are for each epoch. So this is a loss after the first epoch, this is a loss after the second epoch, and so on. Similarly, this is a validation loss after the first epoch, this is a validation loss after the second epoch, and so on. And if you are interested in knowing what is the difference between the loss and validation loss, remember in our history.history object, it printed one loss. This is a list of loss for each epoch, and then it also printed the validation loss here. So I will refer you to this beautiful data science stack exchange question that was asked. Exactly the same question: Keras, difference between val loss and loss during training. And the answer is pretty much that validation loss is a value of cost function for your cross validation data, and loss is a value of cost function for your training data. And this is the main difference. But further, if you go into the detail, of course, I have not discussed about applying dropout, etc. in this video, but dropout is of course a very important part of any deep learning training. So this is another point of difference between val loss and loss. The reason is that during training we use dropout in order to add some noise for avoiding overfitting. During calculation of cross validation, we are in the recall phase and not in the training phase. So we will use all the capabilities of the network. So actually what they are pretty much saying is that during the calculation of loss, the dropout is included, but during the calculation of validation loss, the dropout is not included. But the concept of dropout is a separate concept altogether. I will discuss it in a separate video. But here I just mentioned just to make sure the differences between validation loss and loss in general. So let's go back to our code. Yeah, now the next important point to understand here is evaluation. Oh, but before that, quick point on this val loss again, that Keras could, after the training, it could calculate this validation loss separately, is because during the training, we passed it a validation data set. Let's look at this. During the training, one of the parameter was validation data, and that included my validation inputs and validation targets. So this validation loss, the val loss value, this loss value was calculated on that validation dataset that we passed during the training. Okay, now the evaluation. So evaluation is a process during development of the model to check whether the model is best fit for the given problem and corresponding data. Keras model provides a function called evaluate, which evaluates a model during the training, and it takes three arguments: test data, that is test input data, test target data, and batch size. And all evaluate function will do is to iterate in batches over the data passed and return a list of scalars where the first entry is a validation loss and the following entries are validation metrics. Let's quickly check it actually, otherwise it will not be clear. So here is my code to calculate the validation. First, comment out this. So all I'm doing is I'm using model.evaluate and then passing my validation input, that is test inputs, validation targets, and batch size of 128, and printing these variable that whatever the evaluate gave me. All right, and it gave me loss and matrix array is it just have two numbers, and these two numbers, the first one is actually the validation loss and the second one is the accuracy. So this is an absolute number and this is the actual accuracy. So let's now uncomment this and print this. Yep, that's pretty much it. So the first element of the array from this evaluate model is a loss, and the second element of the array is accuracy. And now finally I come to the final step of any model training, which is to get my predictions from my trained model. And for applying this prediction, I'll be using a predict function of Keras, and to this function I will pass the validation dataset because the validation dataset is the one on which I want to apply the trained model to get the validation prediction, that is the predicted value from the input validation dataset. And this is my simple code, prediction model.predict. So this is the most important part. I'm just using this model is already trained and I'm just applying the .predict function on it, and to this I am passing the validation inputs. And let's print my prediction. It should be a numpy array, predictions, and let's run this cell. Yep. Yes, so it gave me a numpy array. This is all the prediction, that is I have a validation input which was a two-dimensional matrix, and from it this is the prediction I got. And if I quickly print their shape, yeah, 1200 is number of samples because that many were my were the sample number of samples from my validation set. All right, so that pretty much wraps up this video. And Before closing, a quick word on my channel that I will be uploading videos pretty frequently on deep learning involving PyTorch and TensorFlow. So if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. All right, see you in the next video.